Hello and welcome to Lecture 7 for ECE 205. So today we're going to continue our examination of linear second order partial differential equations with constant coefficients that are non-homogeneous by extending our previous results to kind of a more general case of forcing terms. Okay, so we have one goal for this lecture, and that is to solve differential equations of this form, where a, b, and c are just some real numbers. A, again, has to be non-zero for this to be a true second-order differential equation, and we're going to assume that our forcing term is written like this, where this exponential term has a constant term here, alpha, and g is going to be some polynomial. Okay, so previously we kind of saw how to do it when in the case where this forcing term was a polynomial. So here, really, the only thing we're adding is this exponential term here. And one could just kind of naturally think this shouldn't be too bad to work with, since we know that the solutions to this thing here are exponentials or sines and cosine type things, right? So dealing with this extra exponential term might not be bad. It turns out that it isn't actually bad. Okay, so again, this is a direct extension of the works that we did in lectures 5 and 6, and we're going to use a lot of the results that we had from lecture 6 pretty explicitly here. So today's lecture will be a good kind of catch up, rework out some examples for the stuff from lecture 6, and a little bit of stuff from lecture 5 sprinkled in there. Okay, so natural thing is, how do we try to solve these differential equations? Well, to solve differential equations in this form, we're going to extend our method of guessing the form of the solution to something that'll work for these type of things here. Okay. In general, this method that we're going to use is called the method of undetermined coefficients. So if you recall from previous lecture, when I was trying to find solutions to a thing where the forcing term was a polynomial, or just to recap a little bit, in this case here, where I had this polynomial, I assumed that my particular solution was of the form of some polynomial, where I had these coefficients that were unknown. And that's where this name unknown coefficients comes in. Okay, so here we really saw a special example of the method of unknown coefficients, and we're going to generalize it a bit further. And also recall that in this case here, we already generalized our work a little bit for polynomials, so it's kind of natural to think, hey, can I make this work somehow for these exponential extra terms here? Okay, so now what we're going to do is we'll look at 6 constructive examples. These examples are directly taken out of the text. So here I'm just going to add some extra commentary that's not in the text that hopefully will be useful, but I am directly covering problems that are in the text and worked out in detail. So if you want, you could look at the text version, or you could look at the video version here. Hopefully the video version helps with me having that little bit of extra commentary, but yeah. The examples that they picked in the book were really good, so that's why I'm sticking with their examples here. Okay, so for the first case, we want to try to find a particular solution to this differential equation, and then we want to find the general solution after we find that particular solution. Okay, so let's go to Mr. Paint version 2, and you'll see what I mean by version 2 in a second, and let's check this problem out. Okay, so Mr. Paint might not look terribly different, but I have my little stylus thing that I tried previously and it didn't work very well, but now I have a new software update, so upon a student suggesting, like, hey, why don't you try a tablet, I checked it out, like, oh, there's an update, so we'll see how well this works. Okay, so how can I find a particular solution to this? Well, I don't really have any tools to try to be able to tackle this. So the only thing I really can do is I can sit here and I can guess, what if, and I'll put G, actually I won't put G, I'll put question mark, nope, I'll just put 1. What if I guess about the form of a solution? So what type of thing could I maybe want to guess here? Well, if I look over here, ultimately I want a function such that when I take various derivatives of it and add them all together with these particular coefficients, I end up with something that looks like this. Okay, so if I didn't have these derivatives here, I could just guess something that looks like something times e to the 2x, particular 1/3 e to the 2x. But since I have these extra derivatives, that 1/3 version won't work, But notice when I take derivatives of things of this form, I simply get a different multiple of e to the 2x, right? So I can use that property that we kind of noticed previously in the previous lecture, and I can guess, and again, this is a guess, it might not work, I'm just guessing. I can guess that I could maybe find a solution of the form e, or some arbitrary constant times e to the 2x. Okay, again, I'm just guessing this because that's the functional form over here. Okay, does this work? So big guess here, does this work? Well, if I wanted to see, well, if this thing is going to be a solution, then when I take its second derivative and first derivative and plug it into here, I would get that it's equal to this thing. So let's just compute the first and second derivatives here and then plug it in. So we'll speed up this process a little bit here so you don't have to sit through all of it. Okay, so those are what two derivatives would look like. So if I plug these into here, I could say, hey, therefore, out of this, y double prime minus 7y prime plus 12y, what would this thing be equal to? Well, here, my y double prime, that would just give me this. So here, I'm going to write this as a 4c. And just to save a little bit of work, I know, actually, no, I won't do that here just because it's the first time you've seen this. So here, that's what I get for this case. And then to this, I want minus 14 times that arbitrary constant that I'll hopefully find a value for what it needs to be later, times this bit. And all of this would be a plus 12 times y, so that's just c e to the 2x. Okay, so this is what this left-hand side of the equation becomes. And if this is a solution, then I need this to be equal to, and again, the need is going there, but I need this quantity to be equal to, over here, this needs to simply simplify to 4e to the 2x. Okay, so the question is, does this simplify? Well, over here, what I can do is I can just simplify this, there we go, simplify this term out. So everything has an e to the 2x in common. So I'm going to take that e to the 2x and I'm just going to pull it out. So I'll just stick it here. Everything has a c in common. So I'm going to get an arbitrary constant here. And then I just get negative 14 plus 12, so negative 2, plus 4, so a 2. So all of this collapses to this. So here, if this is going to be equal to this, well, I can simply solve that for c. So if I take this and set it equal to that, if I put these two guys together, this will imply that c is simply going to be equal to, well, if you just look at it, it needs to be 2, right? Okay, so it turns out here that I made this guess, and again, my guess was kind of driven by intuition from the fact that I have this function over here, and if I take derivatives of e to something, I still keep that e to the something after I do the process of taking the derivatives. Therefore, it could have worked. So here, in this case, it does work with c is equal to 2. So if I put all this together, I can say from here, this is exactly going to be equal to 2e to the 2x. Okay, so let's clean this up just a tad. Okay, so that just gives me the particular solution, but for the second part, I want to find the general solution. So how do I find the general solution? Well, if you recall from the last lecture, the way that I go about finding the general solution is to do that process where I find the characteristic polynomial. So for the general solution, so for part 2 down here, it's kind of weird with the tablet, I want to find the characteristic polynomial. So from here, my characteristics polynomial, charpoly, this thing is simply going to be, well, I'm going to have, from this term, I will simply have a r squared minus 7r plus 12 would be my polynomial. So here explicitly, p of r would be r squared minus 7r plus 12. Okay, so ultimately I want to find the roots of this polynomial to be able to find the general solution, right? So from here, let's see if we could factor that. Well, here I could do 3 and 4, multiply those to get 12. And then if I add those two together, I get a 7. So from here, I could rewrite this whole thing as r minus 3 and r minus 4. Okay, so the zeros of the characteristic polynomial, so p of r is equal to 0. This simply gives me that r is equal to 3 or 4. Okay, so from here, you can either just remember the way that you end up finding this characteristic polynomial was by using that ansatz that I was looking for exponential solutions, or you could just memorize those formulas. But from here, I get two solutions, namely y1 is simply going to be arbitrary number times e to the 3x, and then I'm going to get another term, this y2, which I'm kind of abusing notation with using y1 over there, so just be cautious of that in your own work. But this would be simply equal to c2 e to the 4x. Okay, so here I found these two solutions. I know from our previous work that these are going to automatically be linearly independent, so I don't have to appeal to that theorem 5.3.6, I believe, or sorry, 5.1.6. So I don't have to do that. You could if you want. But from all of this, we can now write that the general solution is going to be, well, one of these terms here, so this guy, plus the other arbitrary term, so here e to the 4x, and then I'm going to add in the particular solution for e to the 2x. So this term here is going to be my final answer. Okay, so that was kind of nice that this worked out, but I don't know if this is going to work out in general, right? Well, I do, but before you see it, you don't know if it's going to work out in general. So let's look at some examples where this thing breaks down. Okay, so just here, a cleaned up version here. So let's look at this example. It doesn't look all that different than what we had over here, right? But the only thing that really changed was this. That couldn't possibly make anything go wrong, right? Right? Well, let's find out. So here I have the same left-hand side that I had before. The only thing that changed was this. So we might think that a good guess, just from our previous work, let's take y to simply be some constant that I don't know times e to the 4x. Okay, let's test this to see if it works. Well, from here I can compute the derivative, so I'll do that. Okay, so there's my derivatives, and now I can just take these and plug them into the equation. So from here, I simply get that the equation becomes, and here I'll automatically do some simplifications. So I'll get a 16 e to the x to the 4th that I'll pull out, and then I'm going to get a minus, so here I'll have a 7 times 4, so I'm going to get a 28. And here I'll also have an e to the 4x, so I'll pull that out, and then I'll simply have a plus 12, and I'll have an e to the 4x. So here I can pull all of these terms out and write it out, like this. Okay, and this, I need this thing to be exactly equal to 5e to the 4x. Oops, I noticed I had an error there. Here I dropped my constants c, so I'm going to retroactively put them in and put this constant here. Okay, so all I have to do from here is cancel out the e to the 4x's and solve for c. Okay, well, this is a problem. If I add all those together, I get 0. So I need to find such a value of c such that 0 is equal to 5e to the 4x. There is no value of c. So this does not work. Well, now what can I do? Well, there's a few kind of natural ways to come across thinking why this ansatz might work, the one that we're getting ready to try. But one of the natural ways is to think, hey, I could take this y and have this e to the 4x, and I could just multiply it by an arbitrary function u and see what u needs to be. Right? That was the idea that we had before of kind of variation of parameters, but just kind of oddball way. So let's try that and see what happens. Okay, so marking that off over there off to the side, let's try the other version. What if instead of picking this first ansatz, I do this new guess? Let y be equal to u e to the 4x. Okay, again, it's just a guess that since this thing failed here and canceled out, there might be some function where this works out. Okay, so if I do this, the derivatives become okay, a bit messy there, but from here we can now clean up this second derivative just doing straightforward calculations. And from here, if I combine all the terms, I end up with... Okay, so now I repeat that standard trick that I did before where I take these, plug them into the equation, and see what happens. So let's just do that algebra here. Okay, so this is the quantity that I want to compute here. Well, all of these terms have an e to the 4x involved in them, so I'm just going to pull the e to the 4x out just to make things a little bit cleaner here. And let's see what we have in common. So my only u double prime is sitting here, so this will be my u double prime. And here, from this first term, I have my 8u prime, and from this term here, I have a u prime. And there's no more u prime sitting here anywhere. So I'll get an 8 minus 7 u prime. So this will simply be a plus u prime. And finally, I have a 16u from here. And then here I have a 4u, and here I have a single u, which is multiplied by this guy here, so a 12u. And if I actually work that out, they all cancel, so I don't have any extra u's. Okay. So from here, I simply have u double prime plus this thing here is what this would simplify to. Okay, this is no longer 0. So this thing might work. So if this is going to be a solution, so if it's a solution, then I'm going to need this to be exactly equal to, and again, need. This isn't something that's inherently going to be true, but I need to find a solution to this equation here. If I can find a solution to that equation, then I'm good. Well, it turns out that since I now have this e to the 4x here, this term will exactly cancel with this term. I can divide by it, and this tells me that u needs to satisfy this differential equation. And if I can find a solution to this differential equation, I am good. But we kind of guessed a solution to equations of this form previously, right? So when I was just playing around with other differential equation is equal to 1 in a previous lecture slide, so just to refresh your memory, and these cases over here, I kind of guessed at what the solution would be. Namely, I used this kind of method of undetermined coefficients to kind of guess that it had to be a second order polynomial. Does it work? So I can take that same idea and I can apply it to this equation here. Okay, so here it's kind of obvious. If I just were to pick u to be a constant, then I get 0 on this side. So I need u to have some x, well, some dependence on x. So from here, we can note, if it lets me write, note that if I pick u is equal to 5x, this works. Why? Well, here when I take its derivative, I get 5, so I get a 5 here. And when I take another derivative, I get 0, so it goes away. So we can note that this thing works as a solution. Formally speaking, you could use the method of undetermined coefficients if you got to this point and really couldn't guess at what it is. But yeah, unless I tell you to use something like that, if it's this simple of a differential equation where you can just see it, you can just pull this out. Okay, so from here, what I've done after doing all of this work is I said, hey, if y has a solution of this form, then after taking derivatives and plugging it into the differential equation, then that function u here would have to satisfy this differential equation here. And that differential equation has a solution, and it's readily findable here. Therefore, I can put all this together, and I know my particular solution from all of this work will simply be this y sub p is equal to my 5x times my e to the 4x. Okay, so there's my final solution here, and this method worked. So previously I found earlier that the solutions here were given just by these expressions right here, right? This e to the 3x, e to the 4x. So what I can do at this point is I can reuse that information and say from here, y sub g would simply be my c1 e to the 3x plus c2 e to the 4x, oops, make that a x, plus my particular solution, this term here. Okay, so natural question to ask is, why didn't this work? It worked before, why didn't it work now? Well, before I had e to the 2x, right? And e to the 2x is neither of these solutions here. And now I had e to the 4x, and e to the 4x is this term right here. So this method here failed because the forcing term that I had over here was one of these functions over here. Okay? So this is kind of case 2 of dealing with these situations here. So let's clean this up, put it in the slides, and continue to one more example. Okay, so there that is in slide form. Let's look at another example. So here the key kind of difference is that in this case I have a different polynomial over here. So let's just check this out and see what happens. Okay, so we know from before that if this term over here is one of the solutions to the differential equation, or the homogeneous version of the differential equation, then we have problems, right? So it might be a good idea, and we have to do it anyways if we want a general solution, but it might be a good idea to try to solve the complementary equation first to try to guess what our ansatz would need to be. Okay, so let's do this here. So from here, our characteristic polynomial, what would that be? Well, that's simply going to be r squared minus 8r plus 16. Okay, and again, we want the zeros of this, so let's just take a look at this and see if it's directly factorable. Well, 4 times 4 is 16, and if I add 4 and 4 together, I get 8. So from here, we can say, hey, this thing has repeated roots at 4. This might be a problem. In particular, it's going to be a problem, right? So if you recall, in the case where you have repeated roots, so just to make things a bit more explicit here, 0, this implies r is equal to 4. In the case where you have repeated roots, you can recall that the solutions, just from our initial ansatz that we made, only gave us one of these. And then we used variation of parameters, or really kind of a slightly different version of variation of parameters, anyways, to find another solution in the form of y2 is equal to x e to the 4x. Okay, so here the ansatz that we used the second time around won't work, and neither will the first one, right? Because this thing's a solution, and that was my first guess. And then the second time, once I solved for u, I found that it was x times this thing, well, potentially a constant sitting there. And neither of these will work, because if I try to look for solutions of that form, this will fail. Okay, so we have to go back to the drawing board here. So since neither of these things would work, I can't guess those. And really the natural thing to do is just to go back and guess that my solution that I want to try to find will simply be of the form u e to the 4x. Okay, so we did these computations earlier for computing the derivatives, so I'm just going to copy over that work. We don't have to rehash it, right? And this is what I found before. And here I just made it a bit more obvious that this is a guess. I didn't know if it would work. So now what I do is I take these and I plug them into the differential equation. So if I do that, then from here, I'm simply going to get that this y double prime minus 8y prime plus 16y, this will be equal to, well, everything will have this e to the 4x, so let's just leave that e to the 4x on the outside. And let's just look at the various powers of, or various derivatives of u. So here I'll simply get u double prime, because it only appears here. And then here I'm going to get an 8u prime. Here I'm going to get a minus 8u prime, so those vanish. And I have nothing there, so there's no derivative of u. And then finally, here I'll have a 16, and here I'll have a negative 8 times 4 for the u term there, and then I'll have a plus 16. So 16 plus 16 minus 4 times 8, well, that's 0. So here I don't even have any u terms, and I just have this. Okay, so this is what that side here of the differential equation becomes. And now, if this is going to be a solution, then I need this to be equal to 3e to the 4x. Okay, well, here this gives me a nice differential equation for u. So pretty directly, this implies, just by dividing by that e to the 4x term, that u double prime needs to be equal to 3. Okay, so here you can just integrate this twice. So the natural solution to this is simply going to be, well, when I integrate once, I'm going to get a 3x. Since I'm dealing with particular solutions, I don't have arbitrary coefficients that actually matter. So I'll get a 3x, and then when I integrate again, I would get a 3 over 2x. So I just noticed that there's actually a typo in the question statement. It doesn't matter in terms of net things, but I'm going to replace this with a 2. And here I want to replace this 3 with a 2 and that 3 with a 2. Okay, so if I make that adjustment, here I just get u is equal to x squared. And again, it doesn't actually make a difference, like, in terms of this method working with the what I pick for the coefficient, but here I want to stay consistent with the example in the text just for consistency's sake. Okay, so here I just said, hey, if this is true, then to solve the differential equation, all I need to do is pick this for u. So I can put all of this together, and my particular solution, y sub p, and let me do this in a different color. So my y sub p, this thing is going to be u, so x squared, times e to the 4x. Okay. And here I also wanted to find the general solution, and here I found these two solutions over here. So pretty obviously these, if I divide one by the other, that's non-constant, so they're not linearly dependent, so they form a fundamental set. So from here, my general solution is simply going to be arbitrary linear combination of those two homogeneous solutions. So this guy here, and then to this, I'm going to add the particular solution. Okay, so that's all there is to this case, and you can kind of notice we've gone through all of the natural cases that you would possibly want to examine for these equations. And what do I really mean by that? Well, if this is a exponential type form, then I either have that it solves the equation like no times, like if I plug it in, it's not one of these solutions, or I get that one of these solutions is exactly this solution, or I get that I have two solutions, this one and this one, that solve it. So I can put all of this stuff together into a nice little algorithm type thing, if you will. Okay, so there we go. That kind of work in slide form here. Okay, so instead of making lecture slides for this bit, because we'll put a more general case in the lecture slides, let's just briefly look at what we have so far. So if I want to solve something like this, where k is a non-zero constant, then there's three options. It could be the case that this is not a complementary solution or a solution to the complementary equation, in which case we find that I can simply find a constant such that y sub p would satisfy this. Okay, so if this is the case and I already have those solutions to the complementary equation, I can simply put this guess in and then solve for a. On the other hand, if this is a solution to the complementary equation, but this one isn't a solution, then you notice that I could make this guess in that one example, and that will work in general. It's not hard to prove it, it's just a little bit tedious there. And then finally, if both of these are solutions, then I simply guess a quadratic. Okay, so this is kind of a summary for this special case. And again, I wouldn't necessarily recommend memorizing this per se, but knowing that you could always guess, say, some arbitrary quadratic equation times an exponential would be a good thing to have kind of memorized down. Now what we're going to do is we're going to look at a few more examples, and we're going to abstract this thing here, right? So when I started the lecture, way back in over here, I said I wanted to solve these where this is a polynomial. So far, I've only considered these cases here where the polynomial is kind of the trivial polynomial, right? Well, trivial in the sense that it was a non-zero constant, so really shouldn't use that terminology here. So now let's look at another kind of more involved case down here and try to solve a case where I actually have a polynomial over here. Okay, so let's just set this up real quick. Okay, so in this case, I'm not asked to find the general solution, so if I can get away without actually having to compute the general solution, that just saves me some computations. Okay, so in light of kind of noticing what worked earlier, I'm going to guess that y is equal to, and again, this is a guess, y is equal to u, or use an arbitrary function, times e to the 3x. Okay, so I'm kind of using a variation of parameters assumption here and having this set up. Okay, so if this is the case, then I want to compute the first and second derivatives, and this is straightforward to do, so let's just speed that process up. Okay, and now that I have these derivatives, I can take them and plug them into the left-hand side to simplify it out to see what I need to be true. Okay, so here I would need my y double prime, minus my 3y prime plus my 2y. What would this be equal to? Well, just doing the kind of quick dirty trick, everything has this e to the 3x that's sitting there. So I'll just pull that out front. Here, my u double prime, again, is only coming from this term here. So I get a simple u double prime. And what happens from here? So here I'll have a 6u prime minus 3 times u prime. And that's it. So here I'm going to end up with a 3u prime. Oops, undo u, oops, undo u. So here I get a plus 3 u prime, and finally just comparing the u terms, I end up with just a 2u here. Okay, so here this is the thing that I get when I plug this guess into this side of the equation. So I need this to be equal to the other side. So here, if I can get my bearings, here I need this to be equal to e to the 3x minus 1 plus 2x plus x squared. Okay, so from here, this gives me a differential equation with respect to u by simply dividing by this e to the 3x term. So here I simply get that u double prime plus 3u prime plus 2u needs to be equal to minus 1 plus 2x plus x squared. Okay, so here I can guess what my solution is. Okay, so I can't pull out a solution out of thin air, or at least I can't. You might be able to. So what I'm going to do is I'm going to make another guess. So here I'm going to guess that u might be just some arbitrary second order polynomial. So I'm going to guess that my particular solution here for u could be of the form, say, ax squared plus bx plus c, where a, b, and c are arbitrary real numbers. Okay, so now that I made this guess, I'm going to take the various derivatives here that I need and plug them in here. So just doing that real quick, here I get kind of the standard, my u p prime would simply be 2ax plus b, and further, my second derivative is just going to be this 2a. Okay. So now I just do the same trick that I did before with doing variation undetermined coefficients to solve a similar type equation. In the last lecture, I plug them in and see what happens. So here, if I do this, if I take this guess and plug it into this equation, what happens? So I'm going to put my work over here just to give me space for this. So if I do this, my u double prime simply becomes a 2a. My 3u prime, that simply becomes a plus 3 times this thing here. So I'll do it in 2 steps just so you can see where it comes from a bit further. So 2ax plus b. And then I have that plus 2u. So this is going to be plus a 2ax squared plus bx plus c. And this, ultimately, I need this thing to be able to be equal to minus 1 plus 2x plus x squared. Okay, so we've done an example here before. Let me check time. Yeah, so just due to time, I'm going to skip over it here. But if you then use this, you can set up a system of equations, and this thing will imply that these coefficients have particular values. So when all the smoke clears and I solve that system, we're going to simply find that my a is going to be equal to, in this case, just 1/2. My b is just going to be equal to minus 1/2. And my c will just be equal to minus 1/4. Okay, so in your assignments, you need to show the work how to go from this I need equation to the thing here. But here I'm skipping over the details. They are presented in the text. So if you want to see the details of how to do another one of these, check out the text there. I just have 2 more examples to cover, and I think I might run out of time, so I'm just going to suppress that there. Okay, so once we do all of this, we've found a solution for these things up here in my guess, right? So if I put all this together, I now know what u is, so I can go all the way back over to here and put all this together. So from here, my particular solution, and different color, so my particular solution, y sub p, this thing is just going to be equal to u. So what is u? Well, it's just this thing when I plug in these coefficients. So pulling out a common factor, I'll have a negative 1/4, which I will pull this component here just to make it a little bit cleaner, times my polynomial that I found, which would be this thing here when you plug in these coefficients into this thing to get the polynomial. Okay, so a bit messy, but the basic idea is all sitting here, right? TLDR, we made a guess of this form because we didn't know what to guess, and in particular, we in general won't be able to know what to guess unless we have the solutions to the homogeneous equation. So from here, we made this guess, we plugged it in after doing this variation of parameter step, and we ended up finding that we needed this unknown function u to solve this equation here. Okay, so that's what the variation of parameters gave me. And then, since eyeballing this, I can guess a particular solution. I guessed a solution in the form of this quadratic equation here. So I did method of undetermined coefficients to compute its derivatives, plug it in, get a system of equations, and solve for the coefficients. After I had that, I did find that I had a solution, so I put all of it together to get my particular solution here. That is a general technique for attacking these problems, but we're going to look at 2 more examples to be able to quantify 2 more special cases that could come up. Okay, so in this case, it turns out to be the case that e to the 3x doesn't solve the complementary equation. So this is kind of the nice case corresponding to the example 1 that we started out the lecture with. Okay, so yeah, definitely check it out in Trench for the details for evaluating out these coefficients here. But yeah, that's kind of the method that we used here. Okay, let's now look at this example here. Okay, so it turns out in this case, this e to the 3x is actually a solution to the complementary equation. So we have some issues that pop up, similar to the issues that we had in the second example that we had in this lecture. Okay, so let's just kind of run through the motions for how we would try to go about solving this via the variation of parameter type method. Okay, so by now your intuition should be screaming at you that if I have something of this form, a good guess, so again, guess, is, that's off. There we go. So a good guess might be to say, hey, what if this y is equal to u, where I don't know what u is, but I'm guessing it's going to be a polynomial, times e to the 3x. Okay, so if I do this, then I need to differentiate everything out. So we've done that before, so let's just simplify it and give you the functions. Here I would have my y prime would simply be a u prime e to the 3x plus 3u e to the 3x, and my y double prime, after I simplify everything out, this will simply be e to the 3x, and here I'll have my standard u double prime, my standard 6u prime, and then finally a 9u. Okay, so there's actually a theorem you can derive based off this, what these things will look like. Don't do it. I mean, you can do it for practice, but don't do it to memorize it. That makes things awful. Okay, so then what I do is after I have this guess, I now plug this into the governing equations. So here I get this as my left-hand side of the equation. Left-hand side of the equation. And this, when I plug in these bits here, what do I get? Well, I'm going to have an e to the 3x multiplied by everything. So let's pull that guy out. And then here, I only have 1 second derivative. So that term goes here. Here, I again have this term here, minus 4 times this term here for my first derivative. So if I clear all of that out, I end up with this 2 times this u prime. Okay, and then I don't have any terms for u once I actually do that arithmetic there. And now I need this thing to be equal to this other side of the equation if this guess is actually going to give me a solution. So from here, just writing this down, this is the equation that I need to be true, this term here. Okay, again, this e to the 3x cancels with this other e to the 3x. So what I can simply do is get an equation for u. So the difference equation that I'll get will simply be this term here. Okay, so for some reason my video recording stuff messed up, so that's why I miraculously typed so quickly. Okay, so here we now want to solve an equation of this form for u. So that kind of begs the natural question, how did we do that last time? Well, last time we assumed that we had a solution in the form of a polynomial and used our method of unknown coefficients. So here what we're going to do is guess that u is going to be some polynomial. But what polynomial should I guess? Okay, so if I let u be a quadratic polynomial, then the fact that I don't have a u sitting here means that the coefficient of my x squared term would be 0 on this side. So a quadratic does not work in this case. Okay? And the reason why I don't have a u over on this side of the equation is precisely because this e to the 3x solves the complementary equation. Okay? Since it solved the complementary equation, I get this cancellation of all the u terms. Okay, so quadratic polynomial won't work. What might work? Well, it turns out that if I simply guess that this has a solution of the form ax plus bx squared plus cx cubed. If I guess this form of the solution and plug it in, then that will work. And just if you kind of think of this from a kind of pragmatic perspective, if I take the first derivative of this, the u prime term will have an x squared term, which is exactly what I needed. Okay? Generally speaking, when you're trying to make these types of guesses to try to find a solution, if you pick a higher order polynomial than what you need, it'll still get the job done with extra work to be able to actually solve it. But if you pick a lower degree polynomial than you need, then it's not going to work. Okay? So here you might ask, why didn't I leave the constant term here? Well, when I differentiate u to get u prime, the constant term goes away anyways. So while you can leave it, it'll turn out that the constant will be an arbitrary constant, which you don't actually need. Okay, so under this guess, I take u and I plug it into this equation here. Okay, so when I do this, I'm already at 42 minutes here, and I've been running late, so I don't want to keep making super long videos. So when I do this, when I plug this into here, I get that a has to be equal to 4, b has to be equal to -1, and c has to be equal to 2. And remember that trick, if you start solving with c first, the highest power here, it makes your life a little bit easier. Okay, so here, just making a note, I have that plugging this into here and solving for the coefficients gives me this. Thus, from all of this stuff here, I can conclude that I do have a solution of the original form that I guessed, and here I can simply let u be equal to plug these things in. So 4x plus x squared plus 2x cubed. Okay, so all together, taking this along with this gives me my particular solution, y sub p is equal to 4x plus x squared plus 2x cubed, parentheses around those guys, all times e to the 3x. And of course I typoed here. This shouldn't be a plus, that should be a minus, and this should be a minus. Okay, there we go. So that's all there is to this. Okay, so what I'm going to do, just because I really deplore making you guys watch super long videos every week, and yeah, it is kind of useful to have these long videos to cover everything and kind of required in some sense. Let's just skip over the next example and go to the general principles here. Okay, so assigned reading, I want you to try to sit down and solve this differential equation here. Okay, so just like in the last example, just to give you some kind of starter hints here, actually I don't need to write it all down, you'd want to assume that your function y would be this thing times u. Plug that in, you'll get a differential equation for u. In that differential equation, it's going to turn out in this case that your u differential equation will not have a u or a u prime term. This is precisely because this term here solves the characteristic or complementary equation twice, right? This thing and then this times x is to be more precise there. Therefore, you want to make the assumption that u is of the form of a quartic polynomial. In particular, some constant x to the fourth plus some constant x cubed plus some constant x squared. Okay, so if you do that and go through all the steps that we've done a couple times here, then you'll chase out to find the solution. And again, this is example 5.4 and 5.4.6 in Trench, so you can check that out if you just want to read it there. But this is the last classification that we have to worry about here. Okay, so if we put all of this together, we can now solve differential equations of this form readily easily, where g is a polynomial. Okay, so we have different cases. So just like before, we'll have three cases. If e to the alpha x is not a solution to the complementary equation, then this thing is going to be what we guess for our particular solution, where q has the same degree as g. Okay, if on the other hand, if I take this and plug it into the complementary equation, I find that it is a solution, but this thing here is not a solution, then I'm going to make this guess here, okay? So again, here, this q of x is going to have the same degree as g, and I just multiply that by this x thing here, okay? So in the cases that we considered, you would have something like x plus x squared plus x cubed with arbitrary coefficients sitting there. Okay, and then in the final case, if both of these things are solutions to the complementary equation, then we're going to look for solutions of this form, again, where q has the same degree as g. Now, nice theorem, but I recommend not memorizing all of these, just because, yeah, it's a lot to kind of memorize, especially if you start considering how many little tedious theorems we have. But instead, just look for particular solutions of this form here, and then form that differential equation for u, and then look for polynomial solutions based off what the differential equation looks like, right? Once you get to that last bit, you can kind of eyeball it to see what type of polynomials you'll need to have in order to get that largest x to the n power sitting there somewhere. Okay, so again, you can memorize it if you want. You can plug and chug and make these assumptions, but I do recommend doing this process here. Okay, so this process, this whole little thing here, is generally speaking called the method of undetermined coefficients, because you don't know what these coefficients are in this q function. Okay, so yeah, we have really three big methods that we've covered now. We have separation of variables and integrating type stuff. Then we have variation of parameters, and we have method of undetermined coefficients. We have also the stuff with exact equations, but just broadly speaking, those are our methods. Okay, so we're going to end with a little bit more of particular assigned reading that I'll give you. So here I want you to find the particular solutions of this differential equation here. Note this differential equation is not of the form of this thing, but it's a sum of those. So if you recall our linear superposition theorem, we could solve this by first solving this differential equation here, and then solving the case where I delete this, and I have this differential equation where this stuff here is equal to just that. I can then find those two particular solutions and then add them together, and I'm good to go. Okay, so keep that in mind, that this, we now have the tools to solve equations like this as well. Okay, so we're going to go ahead and end here because we're kind of at our upper time limit. So I want you to read section 5.4, and for practice, I want you to look at these questions here. Okay, so for reading section 5.4, if you watched the whole lecture video, there's not much reading to do. Just look over those couple details and couple of examples that I kind of skimmed over, just to kind of refresh your memory if you get stuck for those type of questions. Okay, so here's our meme. Variation of parameters, nah. Let's do method of undetermined coefficients. So generally speaking, variation of parameters is much more of a powerful theorem or powerful technique when you're working on things, because you're not really assuming anything about that function u, it's just some function. So it has a very wide scope, but it doesn't really get you at to the end of the goalpost, so to speak, when you end up with things like these differential equations of this form, right? Here, if I used variation of parameters, and well, first I'd have to find a solution. So that's kind of, yeah, I don't have a solution, so you can't even use them, right? So that's where undetermined coefficients comes in to kind of finish off the day, so to speak. Okay, so I hope all of you have a good day and all that good stuff, and I will see you in the next lecture.